So this is a continuation of the previous part. I'm continuing on right where I last left off. Let's go ahead and clean up my desktop. So let me go ahead and open the PowerPoint for part 2. So in part 2, we now get to start the process of configuring the OUU and performing the OUU. Now, there are a lot of PowerPoint slides in this exercise. I'm not going to go over each PowerPoint in detail. This PowerPoint or PDF is available, so I encourage you to go through each slide thoroughly just so you get an idea, just so you get used to the information that's in this document. Going to assume that you've already gone through the PowerPoint slides and you're familiar with a lot of the content in these slides. Now, here we've done an uncertainty quantification on 3 different configurations of the 3-bar truss. The original cross-section areas of the truss members were 1 and 2. So we went ahead and did a UQ. We did a maybe 50 or 100 samples. We ran Nastran 100 times for these uncertain variables. We collected the responses for the mass, the stress, and the displacement. We looked at what the maximum probability of failure was. We found that the probability of failure was actually very small. Here it's 0%, but I think it was 0.00001% probability of failure. Then we did a UQ when the mean of the uncertain variables were the values that were found from the SOL 200 optimization, 0.83 and 0.32. We then found out that the maximum probability of failure is 53%. So this is not good for us because we actually want a design that has a maximum probability of failure of 5%. So by the end of this video, what you'll see, we'll configure an OUU, and then we get the optimal values for the means of the uncertain variables, which are the cross-section variables. But you'll find out that the maximum probability of failure at the end is actually 0.14%, which is less than 5%. So by the end, we will have a safe or structure that will survive the randomness of when you manufacture it. So now, here for those who are not familiar with part 1, let me quickly brief you on what the analysis model is for this part 2. So we are dealing with a very simple 3-bar truss. Here we have 3 nodes. 3 nodes are pinned. The 4th node is free. We apply our force at node 4 in different directions. So we're dealing with 2 different load cases. The uncertain variables are going to be the cross-section area of the 3 truss members. So these variables are the uncertain variables. They have a mean and standard deviation. We also have some responses. In part 1, we started off with mass, stress, and displacement responses. We identified the most critical responses. So in this exercise, we're only dealing with the mass and stress responses. Some of the quantities of interest include the mean, standard deviation, and the probabilities of failure of exceeding the limits on the actual stresses. So in the OUU, what we're doing is we're actually going to control some variables in the uncertainty quantification problem statement. Here, what we're going to do is control the mean of the input variables. So we are going to control the mean of the cross-section area for variables x1 and x2. The mean is allowed to range between 0.01 and 2. And one very important thing, we know the optimal we know a good place to start the optimizer. If you notice that the original values for the cross-section area were 1 and 2, if we start the OUU at these values, it's going to require multiple Nastran runs, but we found the best starting point for the OUU 0.83 and 0.32 for the cross-section areas. So keep that in, or take that into account while you're looking at this. So now the objective is going to monitor the average mass or the mean mass. And here we are going to look at the probability of failure, where probability of failure is when it exceeds the limits on the axial stress. So the limits on the axial stress are from negative 15,000 actually. So let's go ahead and edit this PowerPoint document. Oh, it is actually there, but the strike through is hiding it. So here, this would be between negative 15,000 and positive 20,000. Now, what we do is the following. We knock down these bounds. So instead of considering the axial stress between negative 15,000 and 20,000, we reduce the bounds. And I'll get to that in a moment as to why we did this reduction. So the probability of failure that we consider is the following. We want to make sure that we are within these bounds, negative 14,250 and 19,000, 95% of the time. So effectively, we're saying that limit the probability of failure to 5%. Now, you might be asking, why do we knock down these bounds? This is why. We are using the MVFOSM method to perform the uncertainty quantification. The MVFOSM method employs a Taylor series to approximate the response function. Now, since we are approximating the statistics, we're approximating the mean, standard deviation, and the probabilities of failure from a Taylor series, there's some error that's introduced during the UQ and the OUU. Now, this error is significant enough that at the end of the OUU, we might be told that, okay, this at the end, the final design has a probability of failure less than 5%. Now, because of the error, when we confirm the actual failure, we find that the failure is maybe 6% or 7%. In other cases, rather, it might be 10%. That difference is due to the approximation error that's introduced when we use the MVFOSM method. Now, what we did in this exercise, we reduce the bounds by 5%. And we do this for both the lower bound and the upper bound. You could try using 1%. 1% worked in this case, but this case is a very simple 2-variable problem. For higher dimension problems like 50 variables, you might have to use 15% or 20% to reduce the bounds so you get reliable results at the end. Here, I didn't want to risk it with 1%, although I know it works for 1%. I didn't want to risk it. In your case, you might have to knock down the bounds maybe 5, 10, 15, or 20%. If you have to knock down the bounds any greater than 25 or 20%, maybe the MVFOSM method is not the best method to use for your OUU. Now, what we're going to do in part A of this exercise, we are going to constrain the total probability, the probability that the response is within the lower and the upper bound. What we're going to do in part B, we are actually going to constrain reliability indices. So maybe I should make a note here. Constrain reliability indices. So instead of constraining probabilities directly, we constrain reliability indices. The reason why I want to constrain reliability indices instead, it's because it makes the OUU run faster. It requires fewer Nastran runs. So we'll do that in part B. Here is just a reminder of what I mentioned in part 1 of this tutorial. The starting values of the variables were 1, 2, and then the optimal SOL 200 solution was 0.8, 0.3. So what you find out the optimal OUU solution is often close to the the optimal OUU solution is close to the SOL 200 solution. So what we did in the previous tutorial, we performed a SOL 200 optimization with Nastran. We got the solution from that SOL 200 optimization, and that's the starting point for the OUU solution. You find out that if the OUU solution is close by, the OUU optimizer has to travel just a small distance to get to that OUU solution. Where if, on the other hand, we started off at the initial design of 1, 2, the OUU optimizer has to travel a large distance to get to the OUU solution. So if Nastran, or rather the OUU, ran Nastran 100 times, if we started here with the starting point of the SOL 200 solution, maybe we only have to run Nastran 20 times. So this is one of the many time savers that's discussed in this tutorial. And here's just an example of this. I actually have the exact number of runs documented. So here, if we started at the initial design values of 1 and 2, the OUU optimizer needed to run Nastran 30 times to get to the OUU solution. But when we started at the SOL 200 solution, the OUU optimizer only needed 17 Nastran runs to get to the optimal OUU solution. Okay then, so let's go ahead and jump to the next slide. Right, so just as a quick reminder, some of you might be new to UQ and OUU. If you do have questions, and as long as they're related to MSC Nastran and Sandia Dakota, you're more than welcome to contact me at this email address. Okay then, so here on my desktop, I have physically printed an outline of this PowerPoint. So you might hear me shuffling through some papers. I'm basically going through the instructions for this exercise. So let me look at my notes and review just to make sure I am at the right spot. Okay, so I believe we are ready to start this exercise. So what we're going to do is the following. We are going to continue on from the last exercise. So here you can see all the files that I have from the previous exercise. You don't necessarily have to continue on from the last set of files. You can actually go to the tutorial section and you would go to the part 2 of 2 tutorial. So that would be this tutorial here. You would click on starting PDF files. That would be this link here. And this would give you the same set of files that we have today at the start of this tutorial. But here, let's go ahead and close some of these other windows. So the assumption is the following. The assumption is that you already have your bulk data files that are configured for SOL 200. So here we have SOL 200, 2 load cases, the desobj command for the objective, and so on and so on. If we look at the design model, we have our design variables for the uncertain cross-section areas. The lower and the upper bound are blank. The D-screen entries are going to help you output a lot of sensitivities or gradients. And then just to be sure, here the DSA PRT command is present. So this is going to trigger the grading calculation. So let me close some of these other windows. And let me look at my notes. So we also need the H5 file, and we have that. So here, let's go ahead and get started with configuring this. Let's go to the machine learning web app, and let's upload these bulk data files that perform the sensitivity analysis. And let's upload that. Now we want to set the initial values for the design variables, or the desvar entries, as uncertain variables. So now we have uncertain variables x and 1, or x1 and x2. We go to the responses section and we select the H5 file that contains the results of that sensitivity analysis. Now, as a constant reminder, you can use these buttons here, the arrows, to adjust the width of these sections. Here, let's go ahead and expand the height of these data sets. Here, the first data set I want to select is the weight data set. This is going to include the mass of that sensitivity analysis. It's the mass of the 3-bar truss. Now, it's very important that you select responses from the optimization response data set. These are going to be responses that have corresponding gradients. If instead you selected nodal weight or nodal displacement or elemental stress, these responses are not going to have the corresponding gradients. The gradients are only available in the optimization data sets. So here we go to optimization response R type 1 weight. We select this weight response, and now we have our new response R1 here on the right. Now let's go ahead and click the stress data set. Now remember from the previous part 1, we know we want to consider the stress from element 1 and the stress from element 3. So here we look at the first row. We want the stress from element 1, subcase 1, so that would be this first row, so we click that cell. And then we want the stress from element 3, subcase 2. So here you see the first 3 rows are subcase 1, and then the next 3 rows are subcase 2. And if you look here, element 3 is in this row, so we select that field. And now we go to settings and set this to Dakota. And then once we have that, we go to the Dakota section, and this is where we can configure both the UQ and the OUU. So let's go ahead and look at this. Let's go ahead and set the UQ method to local reliability. Select the MPP search option to none. When it's none, by default, it will use the MVFOSM method. And let's go ahead and do this. Let's go ahead and set the standard deviation for this, which would be 0.04. And as I mentioned before, if you have uncertain variables of your own, typically the standard deviation would be from testing. You would either manufacture your structural or mechanical system 100 or 1,000 times. You would measure each of the cross sections, and you would find the mean and standard deviation for uncertain variables. Or if the system came from a manufacturer, they could potentially already have that information, so you could ask them for that information and they would hand it over to you. Okay, so we went ahead and did the following here. Let me look at my notes and just make sure I am where I want to be. So there might be a deviation here in my... Oh, no. Okay, we are doing this according to plan. Okay, so we modified the standard deviation in this section. Now we need to go to the other tables. So under OUU approach, let's go ahead and select the bi-level approach for the optimization under uncertainty. And let's scroll down to this table. Optimization under uncertainty, select OUU variables. So here, what exactly do you want to vary? We want to vary the mean of the uncertain variable. So here, let's go ahead and click these buttons. And now I can specify what the bounds are for the lower and the upper bound. So let's go ahead and do that now. So the lower bound is going to be 0.01 and the upper bound is going to be 2. And we'll do that for both of these variables. Now here for the initial value, we do not want to start at 1 and 2. We want to start at the better starting location that I've mentioned a few times, 8.372 for E -1. And then for the next one, that's going to be at 3.2830 E -1. Now let me do a quick double check because I want to make sure this is being done correctly. I want to try and replicate the results that I have in the tutorial, so that's why I'm double checking my steps here. So what I want to do, let's go to part 1 because I think that's where I had it. in part 1, I have the values. Okay, so this is what I want here. So here on the right are the results from the SOL 200 optimizations. So 8.372 for E -1 and 3.283 E -1. Okay, so I've copied those over to the initial value column. And we're done with the OUU variables. Now let's go ahead and talk about configuring the OUU constraints. Now this is where you would supply the bounds. So for R2, let's go ahead and type in the lower bound of -14,250 and the upper bound of 19,000. Now remember that we knocked down the original bounds of -15,000 and 20,000 because the MVFOSM method is approximating our statistics of mean, standard deviation, and probabilities of failure. There's going to be an error introduced during the OUU. So to mitigate how wrong or to ensure that our final probabilities of failure are within the desired values, we purposely knock down the bounds to -14,250 and 19,000. Now, a quick reminder, for response R1, which is the mass, do not supply any values in that row. For responses R2 and R3, do not supply any values for this column, probability of failure, on the left and the right. Only specify values for the lower bound and the upper bound for responses R1 and R2. Now, in this next table, this is where you can get to define this constraint, the probability that you're within these bounds. In this case, this is what we are defining. So right now, let's go ahead and make this very important adjustment. We want to make sure that we output probabilities. So here under statistics to compute at each response level, we set that to probabilities. And now for the lower bound, you get a probability. You get this probability. You get the probability that, let's go ahead and see it, that the random variable is less than -14,250. That's going to be PR2, P1, I believe. So let's go ahead and delete this for a moment. So if you look at this column here, R2, P1, that's defining this probability. And then we get a second probability, R2, P2. This is the probability that you're less than 19,000. Now, right now, it's set to use the complementary option, so we need to modify that. Let's go to the method section. Let's go ahead and turn on display selected keywords, and let's go ahead and set the complementary to cumulative. The complementary option gives you different probabilities. So let me go ahead and adjust this. Complementary gives you the probability that the random variable is greater than -14,250 and +19,000 here. Now, the random variable would be R2 for this case. And then remember, we're doing this for a third response. So the third response would be here, and this would be R3. You can think that the random variable is R2. And again, this is covered in great detail in the other PowerPoint slides. So if you're new to all this, I recommend going through the other slides first. Now, this would be the complementary option. These would be the probabilities that we get. But today we're dealing with cumulative probabilities. So we would have probabilities of this form. So let's go ahead and make that switch. Complementary to cumulative. Now, the reason we want to use cumulative, because then we could define this probability. We want to define the probability that we're between this and this is equal to this probability. So the probability that you're less than 19,000 minus this probability. So we're after this expression. So once we set this to cumulative, let's go back to the wizard and let's go ahead and do the following. Let's go ahead and create a constraint. Let's take R2 and R2P1 and R2P2. Let's turn on both of those responses and let's change the scale factor. So here we're saying take R2, multiply by 1.0 and add it with R2P1 times -1. And this is essentially this expression here. So this is the total combined probability that we are after. So that's what we defined in this column. And then since this is a probability of survival, we say, hey, make sure the probability of survival is greater than 95%. Equivalently, this is saying constrain the probability of failure to at most 5%. And since we did this for response R2, let's go ahead and do this for response R3. So let's turn on both of these buttons, turn on the scale factor, and impose the same constraint. So we're done with those probabilities for response R2 and R3, which are the axial stress responses. And now what about the objective? We say we want to minimize the mean of response R1. We want to minimize the average mass, if you will. So let's go ahead and double check and make sure we've done all of this properly. We've configured the standard deviations to 0.04 for the input variables. We've selected the means as variables. We've specified the initial values, the lower and the upper bounds. We want to look at probabilities. We went to the method section and we turned on cumulative outputs instead of complementary outputs. We defined the knockdown lower bound and upper bound values. We configured the probabilities of survival in this case. We imposed the limits on the probability of survival, and we said the objective is to minimize the average mass. Now let me glance over my notes and just make sure I'm going through everything properly. Let's go ahead and quickly jump to the inspection section. Now, the inspection section would give you a blue check mark if everything looks okay. Of course, this is no guarantee, but it's helpful in some cases. Here on the right, we get the Dakota input file. And if you want more information on how to read this input file, it's provided in the tutorial file in the appendix section. You'll notice that we're outputting probabilities for these different response levels of -14,250 and 19,000. We've imposed specific constraints that we define manually with scale factors -1 and 1. And then here you can see what our constraints on the constraints are 0.95. So I believe we are almost ready to go. Okay, let's go to download and download this. Now, while this next OUU is happening, let me talk about what the plan is in the next part, part B. In part B, we are going to constrain reliability indices. So let me do this. Let me start this OUU, and we'll call this OUU probabilities. So let's go ahead and start this OUU. And then let's go back to the PowerPoint and do this. Let's go ahead and talk about what the next plan is. So here again, the tutorial is going through all the steps. It goes in more detail. So if you're new to all this, I recommend going through these slides. And let me go to part B. So there's a second part B in this exercise. We're not starting part B yet since part A is not finished yet, but I want to start talking about the difference that we're doing in part B. Now, if everything went well in this part A, the OUU that's happening in the background, if everything went well, it will converge, but it's going to require 40 Nastran runs. What we're going to do in part B, we are going to discuss a different approach that's going to require a lower number of runs. We are actually going to require 17 Nastran runs to perform the OUU. So that's good for us because FEA takes a long time in certain cases. One run will take maybe hours or days. We need to reduce the number of Nastran runs as much as possible. So in part B, I will describe a different way of configuring the OUU so it requires fewer Nastran runs. You notice that the objective in both parts are not that different. We're essentially arriving at the same solution. So what we're doing in the next part, we are going to constrain what are called reliability indices. So let me do my best to explain what a reliability index is. So I think, what section would that be? Right, so there's a section in the appendix describing what a probability and reliability index is. Let me briefly go over through what a probability is. So a probability is the probability that you are to the left or to the right of a response level. So if you were using the cumulative option, you would get CDF values from Dakota. This is telling you the probability that you are less than a response level. Here, this shaded area is represented by the probability that the random variable x is less than or equal to 20,000. Now, what a complementary option would give you, it would give you the complementary cumulative distribution function, or CCDF. This gives you the probability that you're to the right or you're greater than a response level. So here, this shaded area is the probability that the random variable x is greater than 20,000. Now, the probabilities that you get are CDF or CCDF values. The CDF or CCDF function is giving you the area under the probability density function. So you can think that CDF and CCDF, this is giving you units of area. Okay, this is very important in a moment. So units of area, you're finding the area under the curve. Now, what a reliability index is, let's see if I can find it. I must have a slide for that here somewhere. Let's see if we can find it. Here. So so the first OUU is finishing, so I need to wrap this up real quick. What a reliability index is giving you, it's giving you the distance you are between the mean of the response and the response level. So in this case, let's suppose the response level is 20,000. So we know what the mean and the standard deviation are for the response. So we calculate what's called the reliability index. This is telling you the number of standard deviations between the mean and the response level. So here it could be the upper bound or the lower bound. Now, an important thing about the reliability index, it's unitless. There are no units associated with that, which is a difference, which contrasts the probability, because the probability that I'll call P has area. Now, since we know the responses are normal, an alternative to constraining the probabilities directly is by constraining reliability indices that are also equivalent. So that's what we do in part B. We constrain reliability indices instead of probabilities. So let's briefly look at the results of the OUU. Let's look at the constraints, the normalized constraints rather. At the very end, we want either a negative normalized constraint or something very close to zero. And here we do get something very close to zero. It's 0.000777785. So this is good. This is telling us that all the constraints were satisfied. You notice that the mass has actually increased. And I believe we can use this diagram to explain what's happened. So we started here at the SOL 200 solution. So this was the starting point for OUU. Here, the probability of failure was 53%. So here I actually went ahead and found the actual probability, and here I forgot where the probability symbol goes. We found out the probability of failure was 53%, but we want at most a 5% probability of failure. So here the optimizer has actually had to increase the size of the variables, the size of the cross-section areas, so the probability of failure is 5%. That's what's going on here. So it's increased the size of the variables, it's increased the mass, it's reduced the amount of violation of the constraints so that we're now satisfying the constraints at the end. And here we see the change in the averages of the uncertain variables. Now, at the end of the optimization in the Dakota output file, you get information about the final objective, the final constraint values. You get information about the best values. So that would be this here. So here, these are the optimal solution values for the means, the average or optimal mass, and you get the probabilities of survival, which are 95%. All of this information is in this tab, the Dakota Results web app. If you go to the OUU Results section, you get the same information. So here, you can look at it here. This page will be more important in the second part. So here, just to summarize the result, we successfully performed the OUU when we constrain probabilities directly. Now in part B, what we're going to do, we are going to constrain reliability indices. So that would be the beta terms. Now the reason we want to constrain reliability indices instead is the following. Here, if we look at the Dakota Results web app, we see that Dakota ran, or rather acquired responses 45 times. So it wanted responses from Nastran 45 times. 40 of those times were unique designs, but 5 of those acquisitions were non-unique, so they were duplicates. So the optimizer had to run Nastran 40 times. 5 of those were duplicates, so it just recycled the already existing responses. So in total, we ran Nastran 40 times. What we do in part B, we constrain reliability indices instead. And when we run this OUU, it runs Nastran 17 times. You'll notice that it reduces the number of Nastran runs. So again, the goal is to minimize the number of runs, the number of times we run FEA. So let's do this. Let's go back to the Dakota section. Let's go back to the wizard and let's do the following. Let's delete the old constraints, on the probability of survival. Let's switch to constraining reliability indices. So we switch the statistics to reliabilities. And here in these columns, probability failure, this is where we specify our maximum probability of failure, which is 5%. So let's go ahead and type that in. You notice that in this table, the equivalent constraints are automatically being created for me. They are automatically managed. There's no modification that you need to do. You'll notice that all the inputs here are disabled because they are automatically managed. You notice that the lower and the upper bounds, instead of probabilities of 95% or 5%, it's using constraints on reliability indices. So the values are going to be different. So here in the table, let's go ahead and make sure that we're following the instructions. So right now I'm looking at my notes here. I just want to make sure that I'm following the instructions. So let's go ahead and look at this. Okay, part B. Okay, let's go and look at this. Okay, I think that's pretty much it. So let's go to the download section and click downloads. So we'll rename this directory 3 OUU reliability indices. And maybe we'll do some comparisons with the Dakota input files. So let's go ahead and do this. Let's go find the Dakota input file and move this to the other side. Let's go back here and rename this 3 OUU reliability indices. And let's go ahead and start this OUU. Now, while this is happening, let's do some comparisons between both Dakota input files. So one of the first differences would be the distribution type. So the distribution has automatically been modified for you when we configured this different OUU. Before we specifically said we wanted to output cumulative distribution function values. So here on the left you see the cumulative option, but here on the right we've automatically switched to using complementary outputs. The other difference is in the compute keyword here on the left. The compute keyword was set to probabilities, output probabilities. But here on the right, in the latest OUU, we said, output reliability indices. So we do this with the reliabilities keyword. Here for the lower bounds, you also notice the difference. Here on the left, we are constraining probabilities for survival. Here we're dealing with reliability indices. So the lower and the upper bounds would be different. So here you can see that the lower bounds are going to be 1.6 on the reliability index, and the upper bound is going to be negative 1.6. So here, let's go ahead and look at the results. Okay, now the first thing I'm going to look at are the results of this OUU. So it's going to make sure we are in that directory. Let's make sure we've achieved fewer Nastran runs. So here on the left is the original OUU from the first part. We needed to run Nastran 40 times. But if we look at this latest OUU, we now needed to run Nastran 17 times. We've reduced the number of Nastran runs, which is great. Here we see that the OUU needed responses 22 times. 17 of those times were unique, where 5 of those were duplicates. Here we can look at the objective, the variables, and the constraints, but we'll do this here. Let's go ahead and look at the final design. Do we have a negative or nearly zero normalized constraint value? And we see that the final normalized constraint value is actually very small. Again, we see the variables, at least one of them had to be increased a lot. So we satisfy the design constraints. We see the mass has also increased. Let's go ahead and look at the Dakota results tab. Let's look at the OUU results. So here, the values that the optimizer is looking at are reliability indices, but we want to look at probabilities. So if you click display additional columns, we get the equivalent probabilities of failure and survival. So here we have a mixture of probabilities of survival and probabilities of failure. So let's turn on this button, display all as probability of failure. So now all the probabilities, let's maybe zoom in a little. All the probabilities are probabilities of failure. And here I think I may have made a mistake. Let's go ahead and look at this. I think I forgot to specify the bound for one of these. Here. So here at the bottom right, I forgot to type in a 5 here. Fortunately, that didn't impact the result. But just know that's that's where the discrepancy is. If you look at this table only has 3 rows. We've only constrained 3 bounds. That's because here I forgot to specify this value of 5. So that's why. If we did specify this value, back here it would have been 4 rows, but here it's only 3 rows. Here, let's look at the probabilities. So the first probability of failure, that's 0%. The next probability of failure is 5%. The next probability of failure is 0. And then if we had supplied the 4th value, there would have been a 4th row here, but it's not here. Now, notice that these probabilities are separate. We get one separate probability of failure for each bound. Now, that's one limit when you constrain the reliability index. You have to specify your bound separately, so you get a bound for the lower. I forgot what they are. I think it's this. Right, so you have these separate constraints on the probabilities, but in the first part we constrained the probability together, so that's one of the differences that you see here. Now you might be asking why are we constraining it separately and not together? This goes back to the units. So probability would give you units of area, but we're working with reliability indices beta. Reliability indices are unitless. So while with probabilities, we could simply take the probability of the upper bound minus the probability of the lower bound. We can't do that with reliability indices. We can't do the reliability index of the upper bound minus the lower bound. Can't do that. Again, because one of these is an area term. The area is what's the probability. But the reliability index, it's not an area, it's unitless. So we cannot simply do the beta of the upper minus the beta of the lower. We have to constrain these separately. So beta of the upper and the beta of the lower. So these will have their own bounds, if you will. Okay then, so where are we at? Here we have another option. Even though we constrain the reliability indices separately, this web app will calculate the equivalent probability of failure or survival between the lower and upper bound, A and B. So here in this row, we get the equivalent probability of survival between the lower and the upper bound. It's 94.99% or 95%. Here, since we forgot to specify one of the constraints on the bounds, we only have this probability, the probability that the random variable is greater than negative 14,250, and here it happens to be 100%. So this looks okay. We're within the 95% that we wanted. But remember, these are all approximate. Since we use the MVFOSM method, there is some error in this final value. So what happens in part C, we go through this verification process, and the verification process is relatively straightforward. What we do is we perform an uncertainty quantification for those optimal values. So here, let's go ahead and go through that process. So if we go back to the machine learning web app, let's go to the Dakota section and go to the wizard. Let's turn off OUU. So it's deselect the OUU approach. So there's nothing selected for OUU. You notice that now we only have the UQ section displayed. The OUU section is no longer visible. Here, let's go ahead and do this. Let's go ahead and change the mean value. Let's go to the results of the Dakota OUU. Let's copy the optimal mean for variable x1 and let's paste it here. And let's go to this text file and copy and paste the optimal solution for variable x2. Now what we're going to do, we are going to perform a reliable sampling for the uncertainty quantification, we are going to say run this for at most 50 runs. I'll explain why 50 is a good value in a moment. Now, one thing we wanted to do, or actually I made a mistake here. We actually do want to use OUU. So do this. Set the UQ method to sampling, set the OUU to nested, copy the optimal mean values to these initial values. So what we're going to do is we're going to run OUU for at most one design cycle. We want to use sampling. We're going to run Nastran 50 times to get reliable UQ statistics. So let's go to the method section. Let's go ahead and do one last modification. For the maximum function evaluations, let's type in 1. Let's go to download these files. Now what I'm effectively doing is I'm running the OUU procedure one time, one design cycle, for those optimal mean values. Instead of using the MVFOSM method, I'm going to use sampling for the uncertainty quantification. So sampling, Monte Carlo, and hypercube sampling, this will give you the most reliable set of statistics. So that's what I'm doing now. So here, let's go and rename this for OUU verification max 1 design cycle. So just go ahead and extract the contents. And let's go ahead and run this. And while this is running, let me look at my notes and just make sure everything looks okay. Again, I want to try and replicate the answers from the tutorial file. So that's why I made a mistake here. So let's go in and abort this OUU. So if we go back here to the Dakota section, the wizard, we want to know the actual statistics for the original bounds of negative 15,000 and positive 20,000. So let's go ahead and copy and paste that here. So again, we're using the reliable sampling method for uncertainty quantification. We use the OUU approach to run this whole procedure at least one time to output the constraint values. We adjusted the lower and the upper bound. So let's go ahead and retry this. And here, while that's happening, okay, so it seems that, okay. So there was another thing I glanced over. Here, instead of 50, we actually run this 80 times. So you can make the modification here in the samples input box, or you can make the modification directly, or actually I won't say that. Let me just re-download these files. Let's go ahead and delete the old directory. Okay, so let's go ahead and do that now. Let's rename this. And let's, just to be safe, let's look at the Dakota input file just to make sure everything's been configured properly. So if we look at the initial values for the OUU variables, we are using the optimal solution from the OUU. Now, what about the response levels? We adjusted the lower and the upper bound. So now we're using the original response levels, or upper bound and lower bound, negative 15,000 and 20,000. If we look at the samples keyword, it's equal to 80. So we're going to run 80 Nastran runs. And let me explain why we're using 80. So prior to this exercise, outside of this exercise, we did a convergence study. We ran Nastran 10 times. I think we even did it 5 times. We did it 5 times. We doubled it to 10, 20, 40, and 80. So we ran Nastran 5, 10, 20, 40, 80 times. And we tracked the probabilities. We wanted to see when the probabilities converge. The probabilities converge after about 20 runs. But here we waited 3 iterations, so 20, 30, 20, 40, 80. So we ultimately said, okay, after 80 runs, we get converge probabilities. So that's why we're using 80 today. Okay, in part 1, you may have noticed I used 50. The reason I used 50 is because I didn't want accurate probabilities. I wanted enough runs to get an idea of what the distribution looked like. What did the histogram look like? That was doable with around 40 runs. I had enough resources for 50 runs, so I went with 50. Okay, so let's go ahead and see where this is at. Oh, and I forgot one other thing. I'm forgetting a lot of things in this part too. When you make this adjustment, or something's going on here. Let's go ahead and see what's happening. Here, oh right, I made a mistake again. I accidentally terminated that OUU and I shouldn't have. I thought it was taking longer than usual, but that's correct because I'm running this 80 times. So that's why it was taking a lot longer than normal time. So if we look at the Dakota output file, we'll see that it's running the 80 samples. So here, let's go ahead and do a quick look at that. So let's open Dakota. Okay, so here you see that it's Dakota has requested the generation of 80 samples. I believe we actually have a separate file for that. So let's see if we can find it. So it's either this distribution file or the other file. So the samples file. Okay, so here are the generation of those 80 samples. So here you can see that in one column we have variable x1 and variable x2. So it's created samples 80 times. And I believe, I don't know, let's see if we can find that. Oh, okay, we don't get that other information. Okay, so if we go back to the Dakota output file, we see that it's running Nastran 80 times. It's using a different configuration of the input variables. It's collecting the mass and the axial stresses for the elements, and it's doing this 80 times. So what I'm going to do now is I'm just going to pause the video and wait for all the runs to finish. Okay, we are at sample 56, so we're almost done with this verification process. Now, let me do a quick reminder of why we're doing this. Okay, so great. Okay, so on this slide, in this column, part B, these are the reliability indices and the probabilities of failure that we had at the end. We found out the maximum probability of failure was 5%. Now, we use the MVFOSM method for the uncertainty quantification that involves an approximation of the probabilities, the mean, and the standard deviation. So this probability of failure is a approximation. What we did just now, we configured an uncertainty quantification with one design cycle for the OUU. We ran Nastran 80 times, and in a moment, we're going to find what the actual probability of failure is. Now, if everything went correctly, I expect the maximum probability of failure to be 0.14%, which is well under the desired 5%. Now, if you're using some other type of UQ method, maybe this verification process is not necessary. But if you're using any of the local reliability, or rather if you're using the MVFOSM method, So here, if we use local reliability and we use the MVFOSM method, if you use the MVFOSM method, this verification process, this step is a step that I recommend going through just to make sure that the final probabilities are reliable. Now, the whole reason we use the MVFOSM method is because it's an inexpensive way of performing the uncertainty quantification. Now, if it's inexpensive, that means our OUU will also be inexpensive. So now, here, let's look at the final results. So we look at the Dakota output file and we go to the very end. We find that we've run Nastran 80 times and now we get some results. Now, instead of looking here, we can look at the Dakota results web app and we get the same information. So here we're interested in this final table here, the constraints, where the probability of A and B. You'll notice one thing here, since I added the lower bound, if you recall here, let's go ahead and in part B, I forgot to specify this input box, but then I added it. So now at the end, I actually get a probability that's between both the lower and the upper bound. So let's go ahead and look at that. So here, we are now looking at the probability that we are within negative 15,000 and 20,000. You see that our final probability of survival is 99.86%, but more importantly, our probability of failure is 0.14%. So good, we're matching what we expected here. So good. Our verification has confirmed that our actual probability of failure is less than the desired 5% probability of failure. So part C has been a success. Now, I think we're pretty much done with part 2. Now, I hope you found both parts 1 and 2 helpful. In part 1, we went ahead and did a setup for OUU. We looked at whether or not we could use the MVFOSM method. We screened the constraints. We reduced the number of constraints. We determined the best starting location for the OUU. We configured the bulk data files to output the gradients. And then in part 2, we performed the OUU a different number of ways, all to reduce the number of Nastran runs that were needed. And then at the end, we made sure that our final probabilities of failure are satisfactory. And as always, if you have any comments or questions, my email address is here at the bottom. If you have a question on UQ, OUU, Sandia Dakota, and MSC Nastran, you're more than welcome to contact me. So with that, thank you for watching, and I'll stop here.